Hi, this is a hands-on session on principal component analysis using SAS. In this session, I'll discuss how to perform principal component analysis in SAS. Uh, Before going through this session, ensure that you have gone through the video on principal component analysis theory and preferably videos on exploratory factor analysis and factor analysis. The reason I'm asking you to go to factor analysis before going to principal component analysis is because we have discussed so many things related to factor analysis, which is a similar quantitative techniques like uh, as the principal component analysis, and hence it's recommended that you go through these lessons before going through this one. Well, to start with, let me just remind you that principal component analysis is very similar to factor analysis. Is used for variable reductions. If we have too many variables in our data set while modeling, that's going to be making a lot of issues. So we need to get rid of the redundant variable. How do you know variables are redundant? If variables are highly correlated, we call them redundant variable. For this exercise, I'll take a data set. It's on student performance in school. I have taken the same data set for exploratory factor analysis. If you have gone through that video, you must be very familiar with this data set. I'll talk about this data set in brief. I have got information on the performance of students or school going kids on a variety of things. Mother's education, father's education, family income, then marks in English, marks in mathematics, social science, natural science, vocabulary. Well, there is another variable named as student underscore type. That variable is a different variable which is not part of the principal component analysis. That particular variable will be used later on for predictive modeling or some kind of a modeling wherein I'll try to know that how can I categorize students based on the information their marks and their family status. So what are the categories? 1 and 0. So if a student has a value of, the category has a value of 1, it's a good student. If it's 0, then it's an average student. I'm not going to use student underscore type for principal component analysis because this is going to be my dependent variable, and I don't worry about dependent variable. Rest all variables are going to be the independent variable, and I feel like there is a redundancy in the data set. Of course, I need to check the correlation before before being sure that there is high correlation or there is redundancy in the data. Already have run the Proc correlation. You can run it when you do it. I have run it. Let me show you the correlation matrix. In many places you can see the correlation is well above 0.5. That shows our data has high correlation, something that is not acceptable for modeling, and there is a redundancy in the information. We need to get rid of this redundancy. How do we do that? We can do that by using the principal component analysis. Well, you must be wondering, why are we not using exploratory factor analysis? Well, as I have already mentioned, exploratory factor analysis and principal component analysis are very similar. They are in fact used for similar purposes. One of the main difference between principal component and exploratory factor analysis is that in factor analysis or in EFA in particular, we are more concerned about the latent construct. we group variable and we name the group something. So what happens is that when we build the model, we are concerned about the coefficient of that factor in the predictive model. Okay, in principal component analysis, we don't really care about the grouping much, although we can, give a name, but usually assigning a name to a principal component is not something a good practice. And if we use that in the model, we can only predict the dependent variable. Explaining the coefficient of the principal component is not worthwhile. Why? Because the principal component itself is not explainable properly. If it is not clear now, I'll of course go into the detail later on. Okay, let us just start with the principal component analysis in SAS. Well, SAS has a very interesting feature. You can do principal component analysis using the Proc factor itself. There are two ways. You can do it with Proc factor and Proc Princomp. We'll go. We'll do it in both ways. Proc factor data. I'll use the data students. That's the main difference between EFA and principal component. The method in principal component should be method equal to prin, PRIN. If you remember in EFA, we either left it without, we didn't mention what method is to be used, or you need to mention method equal to MLE, maximum likelihood. If you don't mention anything, then it will of course do the maximum likelihood estimation. But if you're doing principal component analysis, you need to mention this method equal to PRIN or principal, whatever. You can use PRIN or principal. What else I want? I want a scree plot. That's all I want. And then I'll give variables. I'll give the input variables. So these are the input variables in my data set. Run. Let us run this. Look at the syntax. It's pretty much same as the exploratory factor analysis syntax. Difference is that method has to be print, and we also have used scree. Scree is a plot that is used to know how many components to be retained based on the eigenvalues plot. Let us see the result. It says two factors will be retained by the Minigen criteria. The interesting thing is that although it's principal component, it still says that factor. So there is a there is a bit of a difference. There is a confusion in the terms used here. But never be confused. If you have used the principal option, always read it components, not factors. Although it is all written that two factors, but it's actually component. What is the Minigen criteria? It says that if the eigenvalue is greater than 1, then only it is written. So in how many cases your eigenvalue is greater than 1? Only the first component and the second component. In the rest of the components, your eigenvalue is less than 1. What is a eigenvalue? Well, eigenvalue is nothing but the variance of the principal component, and the criteria is that the eigenvalue should be greater than 1. Only the first two is greater than 1. Hence, we will be retaining only two principal component. So out of the 8 variables, we have 8 variables in place. Out of the 8 variables, we'll come up with 2 principal component. So that's variable reduction, right? 8 variables become 2 principal components. The principal components are also variables, right? They are also some kind of variable. So that's the way we do the variable reduction using principal component. There is another way of finding it out, that how many principal component to be retained. That is the scree plot. It plots the eigenvalue with respect to the numbers. You can see the variance explained by the first one. It's very high, way above 1. Variance explained by the second principal component, around 1.7. But the other principal component, the variance explained by the other principal components, is well below 1. So these principal components can be ignored. Well, I have been using this word principal component very often. So what does this mean? Well, a principal component is nothing but a combination of a set of variables. Okay, making sure that the principal component is able to explain maximum variance among the variables. We have used 8 variables. So each principal component is a linear combination, or is a weighted combination of the 8 input variables. Look at the factor pattern. Again, the word factor is used. You just need to read it as component pattern. There are 2 components, component 1 and component 2. If I have gone through the video on exploratory factor analysis, you can use the same methodology to find out the grouping of variable. Okay, but if you haven't, let me teach you again. You compare the loading, okay, the component loading for both the components. For mother's education, the component loading for the component 1 is 0.41, and for that of component 2 it's 0.69. 0.69 is significantly higher than 0.41. Hence, mother education is related to component 2. Similarly, father's education is also related to component 2, and family income is related to component 2. In all other variables, you see the loading for component 1 is higher than the component 2. Hence, the first 3 variables can be grouped together. So that's like the component 2, and the rest of the variable, okay, are component 1. You can see, right? For English it's 0.77, whereas it's 0.23 for component 2. So component 1 is the one related to English score. Similarly, all other variables down below. So English, mathematics, social science, natural science and vocabulary scores are all related among themselves, and they belong to the component 1. Whereas family income, father's education and mother's education are related to component 2. The best thing is to do is to copy all these values, take it to Excel. Wherever you see the component value higher, just color it, okay, in the same color, and then change the color if the component is changing. Like here it's changing, right? So change it to a different one. You'll get to know that which all variables are similar and can be grouped together. Here the first 3 variables are similar and hence are grouped together, and the rest of the variables are again similar and can be grouped into component 1. The variance explained by both the factors. The factor 1 explains maximum variance in the dataset, whereas factor 2 or component 2 actually explains much less than that. We have the final communality estimates. Final communality estimates are nothing but the square of the variance explained for each of the input variable. You can see mother education, 64% of the variance is being explained by the two principal components. Similarly, for further education, 74% of the variance is being explained by the two principal component. Similarly, for English, mathematics, and so on, we that's the way we interpret the final communality estimates in the principal component output. Well, we are interested in the principal component score, and we haven't got that yet. How do we get that? Now it is clear that we have only two principal components that explain most of the things. We don't need to go to the third one and fourth one because they're not very significant one, as we have seen. So we mention this criteria 2 and then out equal to, I'll use another data set to store the principal components along with the input variables. Make sure whenever you are using out statement to save your principal component values, you need to have this n equal to whatever number of principal component you want to save in your data set. In our case it's 2. I'm putting it as 2, much like your n factor criteria and exploratory factor analysis. Okay, you can see to the very right of all the variables you have factor 1 and factor 2. You can rename as principal component 1 and principal component 2. What are these principal components? They are the linear combination of all the other variables used in the input as the input data set. And what are the weights used here? Well, the weights are nothing but, you can see, right, weights are nothing but the factor loadings. So if you, what you can do is that take this value, okay, factor 1, and for the first observation take each weight. So what is the weight for mother's education? 0.10, right? So 0.10 into 3 plus 0.13 father's education into 4 plus 0.11 family income into 2 and so on. So it's a linear combination. It's a sum product of your factor loadings and the corresponding values of your input data sets. That's how we compute the principal component. So once we have the principal components in place, we need not have to use the variables. Instead, we can use the principal components directly in the model building exercises, and that's how we reduce the number of variables from 8 variables to only 2 components or 2 artificial variables. Remember, in the exploratory data analysis, we used to assign a name to factor 1 and factor 2. It's difficult really to assign a name in a principal component because they are very much mechanical in nature, and it may not be suitable to have a name for them. Okay, another way of doing principal component analysis is using Princomp, data students where input variables and then run. Remember one thing here, that so one thing I have forgotten to mention. What about the rotation? We use rotation in factor analysis, right? So what is a rotation? Rotation is nothing but it's some kind of a orthogonalization of the data wherein there is a clear distinction between the loadings, right? So you can clearly distinguish which particular loading belong to which principal component. There are two types of rotation available, the orthogonal and oblique. In orthogonal rotation, your principal components are perpendicular to each other, whereas in oblique rotation, principal components can be correlated in some way. Okay, there may be some correlation, but in orthogonal rotation, there won't be any correlation between the principal components. That's the strict criteria, because we started with the high correlation in your data, so we don't want any more high correlation in the reduced variables or in the artificial variables or in the principal components. Rotation is equal to vary max rotate is equal to vary max. Was there any error? Okay. Well, when you use rotation, you will have the unrotated result followed by the rotated result. We have seen the unrotated result, that is what was there before, and then when you use the varimax, you will have the rotated result in front of you. Now you can see your factor loadings are much better, in the sense that you can clearly distinguish between factor 1 and factor 2 variables. You see the difference between the factor 1 loading and factor 2 loading for mother education, 0.08 and 0.79, huge difference, right? So it clearly says that mother education belong to factor 2 or principal component 2. Similarly, father education belong to factor 2 or principal component 2. There is a clear distinction. There is a the distance between the loadings is very high, right? So that's where the rotation play a very significant role. Okay. Also make sure that the factors or the principal components are not at all correlated. You can check it out also. There are two variables we have seen, right? Take the correlation between them and you will see that it's close to 0. Okay. We can also use Proc Princomp data and then student name and give all the input variables that we have used, and we can just run and get a similar result. You must be wondering, why do we have two procs for doing the same thing? Well, I also wonder the same thing when I learned for the first time. Um, so far my knowledge goes, the two methods are there because both the methods have got flexibilities. Proc factor is more flexible. You have rotation possible here, you have script plots, you have so many options available to you. Proc Princom is something that by default assumes that your principal components are uncorrelated. You cannot have a correlated principal components. Well, the one of the important thing which is looked at in principal component is that the principal component should be in principle uncorrelated. Okay, but sometimes during the research we may need the principal components to be correlated to some extent. Proc Princom cannot handle it, but proc factor can actually handle it because we have the rotate option here. Okay, and there is a slight difference in terms of their estimation. Okay, so what is the difference? Well, in proc factor the estimation happen in such a way that in such a way that the total variance, it maximize this total variance. Okay, and these variables are actually standardized, the input variables. Hence the total variance is nothing but when the variable is standardized, it means that it has a variance of 1 and mean of 0. Okay, how do we standardize? Well, you can watch a video on standardization of data. I have I'll put that video. Just to tell you in brief, standardization of data is nothing but you subtract the mean and divide it by the standard deviation to standardize it. So in a standardized data, your mean is 0 and your variance is 1. Okay, as well as the standard deviation. Your mean is 0 and variance is 1. That is the standardized data. In proc factor, it uses the standardized data and the total variance is nothing but sum of all the variance. Each variable has a variance of 1 because it's a standardized data. So what is the total variance? It's the sum of 8 ones. So total is 8. Whereas principal component maximizes the variance of the eigenvalues. The variance of the principal components rather. Okay. So so variance of the principal component is nothing but eigenvalues. So it makes sure that some of the eigenvalues is maximized. Okay, so that's the main difference. That's theoretical though. We don't need to bother much about it. If you are if you are somebody who need to understand the application part of it, not the the background theory. But we can always get back to the same result. Okay, let us run it first and we'll see what is the difference in the result. Okay, let's go straight away to the eigenvector. Yeah, you can see that in proc factor we used to get only 2 principal components. Rest all principal components are there, but they are not shown in the result because they are not very significant one. As we have seen, the algorithm recommends only 2 principal components. On the other hand, we do not have the luxury of having the recommendation from the algorithm when we use the proc Princomp. It gives all the principal components. How many number of principal component we can have? We can have as many number of principal component as the number of variables. We have 8 variables, so we can have 8 principal components. If you see, the first 2 principal components are actually good enough. Rest all do not have a good factor loading. Or is that wrong? Well, yes, that is the thing. First look at the eigenvalue matrix. The first eigenvalue is 3.88 and the second one is 1.64. But all the other eigenvalues are less than 1. So the best thing is to select the first two principal component. So we will select only the first 2 principal component and based on that we'll group the variables. Okay, so that is the way we do the principal component using Princomp. Okay, the groupings will be same because if you see mother education, father education and family income, in all the cases the loadings are higher than the first principal component 1, right? Hence principal component 2 is a combination of first 3 variables. Similarly, principal component 1 is a combination of rest of the variables: English, mathematics, social science, natural science and vocabulary. Okay, so the results are same, but the values are different. The factor loadings are different. And that is the reason. What is the reason? I mentioned that previously. The estimation method is different. Proc factor uses total variance, maximizes total variance, and proc Princomp maximizes the variance of the orthogonal principal components, and that's the reason why there is a difference in the loadings. But of course we don't really bother about the loadings much. We bother only about the grouping of the variables, right? Now, one thing that I'll show you, that how do we ensure that the results are consistent from both the procs? Well, just to show you an illustration that you don't need to understand this, just to show you an illustration that they are essentially same. Sometimes we may have a confusion, and we do not need to be very confused. I'll show you that proc factor result and proc principal component results are exactly same, even in terms of the loadings. Remember one thing, principal component value for mother education is 0.20, and for Princomp 2 it's 0.53, and we'll run proc factor and let's see what are the values. Okay, there is a difference in the scaling. Okay, because of the difference in the estimation method, there is a difference in the scaling, hence we have this issue. Now let us let us use this code, proc factor data students, and then we're scoring. We are getting output for all the principal components here. We are forcing it to give all the principal components input variables, and then we have used ODS output, where we have got the standardized coefficients in this particular data set, COF, standardized coefficients. Then we standardize the factor score. Okay, we have factor score from factor 1 to factor 8. We standardize these factor scores, and then we print the output data. We have used a standardization factor, the scaling factor, which is 1 by square root of n, where n is the number of variables used. It's confusing, but you don't need to understand this code, because it's not required during in the principal component analysis. I'm doing this illustration just to show you that the results are consistent. Let me run this code. You can learn this, of course, when you have fairly good command over the principal component analysis. Okay, let me show you. Yeah, this result is from the proc factor, and look at the loading on factor 2. It's 0.20. Remember what was the loading from the Princomp? It was 0.20, right? But earlier, when we ran proc factor here, the loadings were different. What we did here is that we just standardized the factor scores or the principal component scores. That is the only difference. We just need to standardize it in some way, so that there is consistency. But we don't need to do it, because factor loadings are not very important for us. What is very important for us is the principal component values and the groupings. Okay, and these things are not they don't get affected because of the change in the factor loadings. Hence, the conclusion is that you can, instead of using 8 variables, you can use the 2 principal component score that you have saved in your data set. Here in the student 1 data set, you have saved your principal component. If I want to categorize student into good and bad, I can take my dependent variable student underscore type. Let us go to the okay, so I can use student underscore type as my dependent variable, and then as my independent variable I can use component 1 and component 2. I don't need to use any of these variables. Okay, that's how we reduce the number of variables. To summarize, principal component is very similar to exploratory factor analysis. There is a great amount of chances that you might confuse both these techniques. Remember, they are essentially the same in terms of their uses, but the underlying assumptions are different, so you need to be a bit careful. There are two procs available in SAS: proc factor, proc Princomp. You can use. When you run both the procs, you will see different factor loadings or principal component loadings, but the groupings don't get affected. So you need not worry. You can use one of them and save your component score in your output data and use that in the model. Okay, so that's about principal component analysis in